Okay, so we're going to begin with the PowerPoint. First one, we good? The conditions. Second one, calculate the test statistic. Now, we're talking about a mean. So the test statistic will be the t-value, not the z-score, the t-score. The p-value is the probability of getting that t-score you got or more extreme by chance alone, meaning by sampling variability, had the null been true. Perform a test, use a confidence interval. Well, the confidence intervals are reviewed. We did that in chapter 8. This is new. Power of the test. Okay, but that's really for tomorrow. There we are again with the conditions. Except we're talking about means now. So you don't have any proportion to multiply by the sample size that's to be greater than or equal to 10. So instead of that, we're saying the sample size is large enough, greater than or equal to 30 for the condition. If it's not, well, you could draw it like you would use a box plot to say that it's symmetric. But even if it's not symmetric, you still keep going, still perform the test, and then you note that you didn't meet that condition. And this is saying it's not enough to make the graph on your calculator. You have to draw this freehand as part of your template. So we saw this problem before. You have 15 batteries, and you want to check and see what the mean lifetime of these batteries are. Check to see if the conditions are met. Well, you have an SRS, and 15 is less than 10% of all the AAA batteries. The other condition is the sample. So the sample's 15. It's less than 30. So you're going to have to do a sketch of this. Now, the most efficient way for you to do this in May and in our class moving forward is to do a box plot. I don't care that they did this dot plot. You would do a box plot and just reproduce that in your template. The standardized test statistic is your t-score. Now, in theory, it could be a z-score. See, z's go with proportions, t's go with means. But if you knew sigma, if you knew the population step, you could use a z-score because then you could fit it to the normal curve. That's very rare. The only example that I can really think of are the AP scores. Okay, when I'm figuring out our standing, our percentile on the AP results, I use a z-score because College Board publishes sigma, the population step. That is very rare. Okay, because the population step is almost always unknown, we use the sample standard deviation. And then what happened? Contrast these two formulas. The difference is instead of sigma, you have the sample standard deviation. Instead of the parameter, you have the statistic. So instead of getting a z-score, you're getting a t-score. When in doubt, ready? If you see a mean question, you're going to assume that you're using a t-score. And what? Well, we mentioned this before. This is not the first time you're going to see this. Well, it's not the first time you've seen it. It won't be the last time. Degrees of freedom. for the context of what we're doing, the degrees of freedom are one less than the sample size. Okay, and if you need to do this, you come back to section 8.3, which was a confidence interval about a mean. And that's when they introduced degrees of freedom to you. And again, this picture was in chapter 8. So the standard normal curve is the purple curve. And what happens? You push down on the purple curve depending on the degrees of freedom. The more degrees of freedom, the less you push down on it. So that if you had a high, you had 1,000 degrees of freedom, because you had a really large sample size, then it's going to map onto the purple standard normal curve. But the t distribution accounts for lesser degrees of freedom, and this picture is showing you the smaller the degrees of freedom, in effect, the smaller the sample size, the more you push down on the curve, which pushes the tail out. T distributions have more area in the tail. Okay, but we've seen this slide. Should make sense to you. And if you look at the back of the book, which we're not really going to focus on, because you have the calculator to do this, but if you look at the back of the book for that table on the table for the t distribution, when the degrees of freedom are really large, the t scores and the z scores are the same. So, batteries. We're testing to see. The null is that the average life of the battery is 30 hours. The alternate is we have better batteries and it's greater than 30 hours. So what happened? Well, look at these numbers. You see where they're coming from? Your sample statistic was 33.93. That's better than 30. Yes, but is it statistically significantly better? So the numerator is how far it is away from the null. Here was your sample standard deviation divided by the square root of the sample size. The degrees of freedom are one less than the sample size. And you got this z score. I'm sorry, this t score. Now, ready? Here, they're saying use the table. And they get these values. For where we are, 1.55 is between 5% and 10%. Okay, we're not going to do it that way. We're going to use the technology to get the p-value. Table B has limitations for finding p-values. We're not going to use table B. Now, you could get a question, right? You could get a question in May where it was written like this, in this context. So you have to be able to read the table, but you're just not going to use it in practice. But then it says it gives you 1 to 30, and then the change is 10 after that. You get to 60, then it goes to 20, it goes to 900. Use the next smaller ones available. Well, ready? This is kind of helpful in that if you got a question like this in May, and they ask you to interpret the value there, you would go to the next lower number. That's the way it would be written in a multiple choice question. You'll see what that means as we move forward. So, suppose you want to do this. The null means 5 versus it's not 5. So it's a two-tailed test. not equal symbol. Mouth is 1%. Here's your sample size. Here is your sample mean and your sample step. So this is a comprehensive test for a mean. This is where you have to do this. You'd have to do all the parts of the template. This is an inference question. Okay, this whole thing. There's a date in here to do an inference question. So, what did we get? This is not something you would do on the test. We got 4.81, which is not 5. So it's less than 5. But is it less enough that we consider it significant? So here's your t-score. You understand where they're getting these numbers. 4.81, which is the sample statistic, take away the null, 5, over what? Over this sample standard deviation divided by the square root of the root sign. That's your t-score. Whoa, negative 3.17 is really extreme. 36 degrees of freedom. Now, we're not going to do this. We're going to do this on the calculator, but look what they're saying. For this 3.17, you're way over here. Look at these confidence levels, 99.5 to 99.8. You don't even need to look at this. If your t-score is that extreme, you can pretty much look at this and say, I have to be in the tail. So here's the technology. They doubled this because they used a normal, they did a t distribution to get the area. Right? We're not going to do that. You don't have to double it. You can just use the t-test on the stat test menu. But you're getting 0.5%. The area of the, this area right here, after you double it, is only 0.5% because it's a two-tailed test. And then here's how we're doing this. Actually, we're not doing this. We're going to just use the test menu. But you could do, the cumulative distribution function for a t-score. And then here's an arbitrarily high number, and there's the degrees of freedom. But again, you don't have to do this. You don't have to do this. You can focus on the stat test menu. Because this doubling here is not something you need to get involved in. So this is the template again. And then they're going back to this and saying, okay, well, here's the algorithm for a t-score, and here's how it's affected for each of the conditions. Okay. And then again, we've seen this picture before. This picture here, one-tailed test, two-tailed test. An equality symbol, not equal to symbol. Let's see where we are with this. So how about this problem? There's 15 randomly chosen locations. And they want to see what this oxygen level is. So we're not going to put this in the calculator. We're just going to watch what they do. They're picking a 5% significance level. So do the template and then say, well, what kind of error could we have made? So we want to test where the mean is 5. It's a one-tailed test. because it's a danger if it's less than 5. Say, do the data provide convincing evidence at this level that the aquatic life in the stream is at risk? See, not equal to 5 doesn't make sense, because if it's greater than 5, it's not endangering the aquatic life, the fish. So we're doing a 1 sample t-test, 1 tail test. 1 sample and 1 tail are not the same thing. You don't even have to write 1 sample. You write t-test for mu. All right? SRS, 10%. We don't have to worry about this sampling, the sample being too large. Except, what about the sample size? It was only 15. So they have a histogram. Again, we're going to stick with box plots. So here's what we get. Here's your sample statistic. Here's your sample step. Here's the t-score. How far you are away from the null, your step divided by the square root of the sample size. Gives you this z-score. Well, you can tell by the picture. You're in the body. You're going to F2R. Okay? So what's the number? The area of the curve is 18%. The p-value is greater than the alpha level, so we fail to reject the null. Now, it's below, ready? This number, 4.771, is less than 5. That could be attributed to sampling error. It could actually be 5. There's an 18% chance that the true mean of the oxygen level is 5 or higher. And 18% is not enough, not a great enough probability to reject the null. We do not have convincing evidence that the true oxygen level is less than 5. Now, what kind of error could we make? So think about this. What did we do? We failed to reject. That's where the F2R is helpful. You failed to reject the null. So you could have made a type 2 error. We can't get that wrong. Right? The only way you can make a type 2 error is if you fail to reject the null. If you reject the true null, that's a type 1 error. And we're going to, you're going to do this. You're going to use the template to do this. So here we are. So here's the template. And again, this is in the chapter 8 and the chapter 9 Canvas folder. And when we're doing these problems, like when we, do the inference questions to be graded on through AP Classroom in the spring, I expect you to be using this template. Conditions: SRS, random assignment of treatment. Okay. The sample size is greater than or equal to 30, or you draw a box plot, and your sample is less than 10% of the population. There's T, okay? And we could do inverse T. We can get the T-score if we put the area in the degrees of freedom. And then we can use a Z-score, but it's unlikely that we would know sigma. All right? So we're going to pause this, and you're going to one pair of problems, 69 and 70. First data set. It says assume the conditions are met, even though 25 is less than 30. How far are we from, ready? The difference is one question is a two-tailed test. Another question is a one-tailed test. So here's how this looks. Ready? Your sample mean 62 and 8/10. How far is that from the null? 64. Your sample standard deviation is this divided by square root of the sample size, 24 degrees of freedom. So I'm saying, okay, if we do this way in the left, which you don't have to do, you would get this t-score. The area under the curve to the left to this t-score is 1300ths. The two-tailed test, you double it, you get a p-value of 0.27. You don't do any of this. You just go to the t-test. Now, the issue is, when you go to the t-test, the input is data, meaning if you use a list, or the summary statistics, which is how we did this. So I put in those numbers, I pick a two-tailed test, and I get the same p-value, 0.27, without having to double it. Okay? Fail to reject the null. There's a lack of evidence that the parameter is not 64. Well, I didn't know how to do this on the t-test. That's fine. You would just do it this way. Like, this is the shortcut. There's nothing to that. This is what you have to understand what the value of the test statistic is. And for 70, again, it tells you assume the conditions are met. Here's the calculation. But this is a one-tailed test. So we want to know if we're testing that it could be less than 5. So we're at 4.7. This gives us a t-score of negative 1 8/10. The area of the curve to the left to negative 1 8/10 is 4%. It's a one-tailed test. We're not doubling it. If we go to the t-test, right, we pick this inequality instead of not equal to, and you get this p-value, which is less than 5%, so we reject the null. So in this problem, there is statistical evidence that the parameter is less than 5. Okay? So that's that for the alpha lesson.